Thank you very much. My sound, I'm on. Camera in the back, I'm cool, I'm good to go. It is crazy. I dare to say one of you. I'm a product of the University of California. Fiat lux is my motto. And yet it took me so long, it's embarrassing, so long to come here at last. And it's just been a day, and it's been such a great day. I'm planning to return quite likely in February, but already my meetings, my interactions with you, with the students, have been inspiring. So I can't wait to come back, but I also can't wait to address various interesting aspects of galaxy scaling relations with you. It's a little bit of a challenge, of course. It's a colloquium, so there are people who don't necessarily do astronomy in this room, condensed matter physicists, or students who are coming from a different field, and I want to make sure that I'm appealing to all, okay? So the introduction is a little longer in the sense that, again, I want to make sure that we all, follow, but do stop me, of course, at any time. The most important question, I guess, anyone should ask when you see this slide is, where's Queen's University? We're going to ignore that screen. It's not working, and so I'm going to focus on this screen, okay? So where is Queen's University? Some of you may know. I would, again, speculate that if you do particle physics, you may know about Queen's University. So we're here in Ontario. You may hear a certain accent. I'm from Montreal. I'm French-Canadian. So Montreal is right here, and we're very close, okay? So Ontario is here. Syracuse and Rochester are just below us, and Kingston, Queen's University is on the shore of beautiful Lake Ontario, beginning of the Thousand Islands here. Toronto is over here. Montreal is up here. We're equidistant between those two cities, Rochester, Syracuse, to give you comfort in an American background there. You may have heard of us largely through this 2015 Nobel Prize in Physics for the demonstration that neutrinos oscillate and therefore have mass. It's shared jointly with Super Kamiokande. SNO Lab is, SNO stands for Sudbury Neutrino Observatory. Sudbury on this, where's Toronto here, you drive 4.5 hours and you're in Nickel Land. That's where the mines are. You want to go deep underground and go down with the miners. They go this way, you go that way in your ultra clean lab, which is the Sudbury Neutrino Observatory. And that's where measurements in the 90s were made by a group led by Art McDonald to demonstrate the oscillatory nature of neutrinos. Since then, the group is expanded and includes a lot of particle astronomers who focus on detection, on theoretical aspects of particle astrophysics, and people like myself, more sort of classical astrophysicists who worry about the distribution of dark matter on large scales. So that's what I'd like to discuss with you. How can we infer about the properties of dark matter just by looking at properties of galaxies? Oh yes, Flip mentioned this conference that I organized. It was quite exciting to celebrate the achievements of giants of cosmology, both on the theoretical side and observational side. And I organized this conference wanting to bring together particle astrophysicists, theorists, and observers to see if we can arrive at a common framework of dark matter and where we're going with future studies of dark matter. So we celebrated, the screen is a little fuzzy, the careers of, you may recognize some of these, again, pioneers of the so-called cold dark matter modeled, Dick Bond, Sandra Faber, who was my advisor, university professor at Santa Cruz, Ken Freeman, Jim Gunn, Rob Kennicott, John Cormandy, Jim Peebles, Joel Premack, also at Santa Cruz, Brent Tully, and Mike Turner. So again, it's always If you've organized conferences before, you know that you achieve success when you have a good scientific idea to debate and you can celebrate people at the same time. Those are typically called Festschrifts, and in my view, they lead to very interesting debates and discussions. So when we think about galaxy formation, it's always fascinating to realize that out of really complicated astrophysical processes, you obtain galaxy scaling relations that are especially tight. Okay? There's regularity in a system that emerges out of nearly chaos and complexity. So you start with a cosmological model that's purely dark matter, and then you let galaxies form. They do so through mergers and interactions, and eventually you need to form stars. You need baryons to fall in dark matter potentials. You form galaxies, and that process is a little dirty and certainly poorly understood. You have star formation, feedback, the implementation of energy in ejected and injected energy in your galaxies and clusters of galaxies, bursts that ultimately regulate the size of galaxies that you will measure in the present day universe. And as you'll see in this presentation, you get incredibly tight scaling relations. How can that be? You start with purely dark matter, and then you throw in baryons, and yet these two quantities, components, talk to each other in a way that we don't understand particularly well. So the title of my presentation might have just been not just scaling relations of galaxies, but puzzles in galaxy scaling relations, and I'd like to introduce a few of them. So when one looks at scaling relations, in just a mathematical sense, it's just a correlation between two variables, x and y, and those variables for us in studying galaxy structure can involve a variety of observables that pertain either to star formation history, age and metallicity, abundances, dust, masses, winds, AGN, which stand for active galactic nuclei, supermassive black holes in the core of your galaxies, which regulate some of these quantities. I could pick any of these, any pair of these different observables and cook up some interesting model, okay, and talk about them ad nauseum. For now, I'd like to focus on those scaling relations that are dynamically rooted, because we know that dynamics, or the mass of a system, typically prescribes the evolution of a system in addition to its environment. Okay, so we'll focus on these scaling relations that enable correlations with a dynamical quantity, be it a rotational velocity or a dispersion, the mass of the galaxy. Ideally, when you want to understand these complex systems, you'd like to restrict your model, your analysis, to the simplest observables. And the simplest observables when you study galaxies or stars or celestial objects are size, velocity, luminosity. Out of those three, you can essentially reproduce all the different scaling relations that we see. Colors will inform you, luminosity in different bands will inform you about colors, which also will inform you about stellar populations. Velocities and size combined will inform you about mass and dynamics. The typical scaling relations that I'll talk about, and also the most popular ones, are combining these guys, doing linear combinations of these parameters. So you can have velocity, luminosity. That's also known as either the Tully-Fisher relation or Faber-Jackson. Tully and Faber were amongst the 10 VIPs that were celebrated at this conference this summer. What's particularly special and mysterious about these relations is you have one that depends essentially entirely on dark matter and another one that depends on baryons, and yet, as you'll see, they conspire to giving you a very tight relation. Baryons and dark matter talk to each other, and it doesn't make sense because they are not allowed to necessarily interact, right? Dark matter does not interact via the electromagnetic force. It's strictly gravity that sort of couples these two components, and we need to understand how and why. So we can do size luminosity, we can do size velocity. We can also not just build scaling relations, but distribution functions. How many galaxies did our universe form of a given luminosity, of a given velocity, and of a given size? So these luminosity functions tell us very much about the process of galaxy formation. There are experts here who also study the effect of supermassive black hole and feedback the energy injected by these black holes and accretion disks into the interstellar medium. They affect very much the evolution of galaxies. I must say, I won't talk about them very much. Very sorry about that, but for lack of time, we will stick mostly to global scaling relations. An interesting development of the last few years is the realization that local scaling relations, also local meaning spatially resolved. What sort of information is the center of the galaxy or the middle part of the galaxy, like where we are in our galaxy, or the outskirts, tell you? Do they give you consistent pictures? Some very fascinating trends are emerging. So that's local versus global. And I'll say a few things about local, but not too much, mostly global. So the ensemble of patterns that we see, these correlations that we see, again, inform us about the structure of these galaxies and hopefully about their evolution. Can we, from the scaling relations of evolved galaxies, infer something about their history, their merging history, accretion history, as well as the nature of dark matter? I won't have time to cover it all, but those are the topics that we addressed this summer at the conference at Queens, and I would not claim to say that this is a summary of our conference. It would take too long. Some of the ideas that I present here are inspired from some of the debates and discussions that we had at Queens. At lunch and with the graduate students, we were talking that some of the biggest challenges that we have often in science is making sure that the theorists and observers agree on definitions. How you measure a particular quantity and making sure that the theorist appreciates how it was measured and the observer appreciates that the theorist really needs this particular quantity. That's always a challenge, and it remains so. My advisor taught me very much that way, and I'm teaching my students that way as well. And I know, having organized this conference, that it's still very prevalent. There's confusion in the field. So if you allow me, I'm going to take 5 minutes to explain how we measure the size, the luminosity, and the circular velocity of a galaxy, because I know there are experts in the room, and even amongst all of you experts, I give you a galaxy and I ask you to measure a size, we're all going to get different answers. And likewise for velocity and luminosity. I want to state those definitions so we all appreciate what we're trying to do. For instance, if you see that the majority of disk galaxies like this one here, with its name UGC 9908, that's its luminosity profile. The axis here is a luminosity, okay, with bright at the top and faint at the bottom, center out, okay? So it's bright in the center and it decreases, and because this is a log scale, this straight line here means that it's an exponential profile, okay? Spiral galaxies have exponential disks. We could have an entire colloquium on why that is. How is the universe or galaxy formation making these exponential disks? It's super interesting, actually. But we'll leave that for another discussion. However, out of these profiles, we may say, can I measure the size of a galaxy? Well, if you look at this profile, it stops right here, at a certain radius. But I know it's not, that doesn't define a size. The problem is galaxies have no edge. You can keep going and finding stars that are still bound to that system, and eventually the notion of edge becomes so fuzzy that you give up. So what astronomers do is, rather than measure a physical finite edge, You measure a scale that tells you about the steepness of this profile. It's called an exponential scale length. So if you have the exponential profile here, this quantity here, RD, is an exponential scale length, and it simply tells you about the steepness of this profile. The intercept of this equation here is this quantity mu naught. I'm spending an extra minute to explain that that mu naught will return in a few slides, and this is going to be our first puzzle. The distribution of mu naughts in galaxies is bimodal, as you'll see. Even better, we tell our students, I don't know about you, but certainly I try to avoid as much as possible parametric modeling. I don't like it. Because once again, if I give this profile to you and you're going to come up with two different parameterization and different results. Non-parametric science is so easy. We can all agree on, right? Non-parametric meaning I do not impose a model. So an example for a galaxy for a size, a non-parametric quantity is just to say I take the total light, I count where I get, say, half the light. It's arbitrary, but everyone agrees on half. And that gives me an effective radius, okay? So you eliminate personal bias. Another one that we use is so-called isophotal radius, you know, where you get a certain surface density of stars. I'm spending a lot of time on this, but you'll see why, and it's useful. Rotation. Rotation of galaxies is key in order to understand their masses. You have a spiral galaxy here. You put a slit on the major axis of the galaxy. Doppler shifts will inform you about the rotation of the stars and gas in that galaxy. For instance, here you have the emission line of H alpha that's being shifted by Doppler effect. This tells you, so here's the same line H alpha, flanked with nitrogen 2 on both sides. You could look at different lines. They better give all the same consistent picture of rotation curve. And you want to measure a characteristic velocity for this, and you appreciate as an observer that it's very noisy. Theorists will just fit a line. And I know that the act of fitting will actually bias the result. Okay? You've got to be careful. Maybe a little bit of a technical slide here, but when you get the rotation curve, what you observe is never really the true reality. See, you need a tracer to tell you how stars are moving and how gas is moving in galaxies, but those tracers are biased. And they're biased in a very challenging way. Gas is viscous. So gas tends to stick a little bit together, and that causes non-circular motions. So as a theorist, you can reproduce. This is Newton telling me there is this much mass within my volume, V squares GM over R, that gives me V. But as an observer, I know that the gas will always give me a biased picture, and the stars even more so. The stars age over the course of their lives, and they start lagging behind a young star like the sun. It's called asymmetric drift. Okay, so these effects are actually significant. They match at, this is a funny scale here, but in the outskirts, they're all equal, but typically we make our measurements here. If you don't account for these effects, you get somehow a different theory. And you may say, hey, I got a new theory of dark matter. No, 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 you don't. You did not account for special important effects. Okay, enough for my introduction. I don't know when I started, Flip, so you're going to keep me. It's 4:05. Okay, let's move on. The point about this is you need to be very careful about how you make your measurements. I could go on and on, as you can tell, about that, but one must be careful. So I want to talk about these very important relations in astronomy, Tully Fisher and Faber-Jackson. They tell the same story. They tell that the circular velocity of a galaxy is proportional to the luminosity, the luminosity proportional to V to the third or fourth power. This is a circular velocity. This is a velocity dispersion. These two equations essentially tell the same story. The protagonists are here. There's Tully and Fisher. There's Faber and former graduate student Jackson. Tully is in the middle. And other people over here. So what do these relations tell us? Again, what's so important about them is in a few minutes we'll realize that these are very tight relations. Here we have a quantity that depends, that's regulated by the potential, by dark matter. Here we have just baryons, and you'll see it's not just a parallel, it's a tight parallel. And why is that so? Oh, sorry, I keep flicking back and forth. Originally, Tully and Fisher appreciated that out of a not only dark matter dependent quantity, but a distance independent quantity, the velocity, the circular velocity of a galaxy has nothing to do with its distance. So whether it's close to me or far away, it's still going to have the same v. The luminosity, though, will be affected by distance. So this is what you call also a distance indicator. Measure the velocity, measure the apparent luminosity, you get its distance. So the first use of these scaling relations, in fact, was to measure galaxy distances. For the experts in the room, few people know that Faber-Jackson and Tully Fisher were actually discovered at least 20, 30 years prior by Morgan, Mayle, Ivan King, and others, just for name dropping. And all these giants of astronomy as well appreciated that you could use these techniques to get distances to galaxies, right? Measuring distances in astronomy, that's the bane of astronomy. And there's many other effects that conspire to give you wrong distances. But getting distance indicators is very useful. But in the 90s, we started appreciating that we could use these relations to understand galaxy formation. And not only can we do that, we can connect ET. So ET stands for early type galaxies. Think elliptical galaxies. LT is later type galaxies. There's nothing really having to do with time of formation. Think of it as elliptical galaxies and spiral galaxies. They're typically, a spiral galaxy is dominated by circular motion, whereas an elliptical galaxy is dominated by dispersion. It's very difficult, it turns out, to measure the mass of these objects accurately. I give you a spiral galaxy, I give you an elliptical galaxy, I guarantee you're going to get wonky masses. It's, without going into details, it's hard first to get accurate masses. It's a little bit easier for spiral ones, ellipticals are hard. But then what you want is a framework that brings them all together. Because you don't care about how masses are measured, you just want to make sure that you measure them consistently, and then you put them all in a common framework to understand how galaxies form, perhaps in the first place, and perhaps to be informed about the nature of dark matter. Scaling relations may evolve with time. In fact, they do a little bit. I will have to skip that. Okay, no time to talk about that. A few more slides, mostly for the students in the room, about philosophy, methodology when you do these kinds of problems. And we're talking about astronomy here, but any form of science needs this approach to solving a particular problem. In our case, we're looking at scaling relations. Y on X. Well, galaxies are complex systems, and you can think of multiple Ys and multiple X's. You can construct a number of different scaling relations, and if your model of galaxy structure and evolution is the right one, they all must agree simultaneously. There are, I'm sure, people in the room who have taught Tully Fisher luminosity goes as v to the third power, and told their Astro 101 students that's virial theorem, or that's Newton, because I get the right slope. Fine, but everything else is wrong. You can get the right slope for the wrong reasons. You can get the right 0 point for the wrong reasons. You can get the right scatter for the wrong reason. There's a scaling relation is defined by 3 parameters, right? A slope, a 0 point, and a scatter. We know this as, you know, when we were students. There's no greater joy than discovering a scaling relation. And then once you've discovered it, you have to explain those 3 parameters, and you can push your investigation further and then see if there are other scaling relations that are projections of the one you found. So that's a first, fitting all known scaling relations simultaneously is a key endeavor that we're pursuing. And understanding, this one is obvious, but it's good to state it again, understanding biases in your data is critical. There are recent claims based on either scaling relations or some measurables, observables that enter into our discussion that have been made lately to the effect that there's no dark matter in the universe. Galaxies don't have dark matter. And then you go a little bit deeper into it and you realize, well, hold on. You didn't appreciate that your data are biases in a certain way that prevents you from, say, finding dark matter or seeing that it's there. Here's an interesting one. Again, nothing to do with astronomy, but just how we analyze data. I give you two variables. X and Y are completely uncorrelated, drawn out of a random distribution, Gaussian distribution. And what do I do in astronomy? I like to divide them and I plot them against the same variable here. What do I get? A correlation. We do this all the time, astronomers. Apologies for the physicists. We have a name for this. It's called a color magnitude diagram, among others. It's really interesting to start looking at our approach to plotting data in astronomy. We do these correlations all the time. This is a colored term here, magnitude. Worse, you take the log, you get a straight line. And yet, these variables have nothing to do with each other. So, again, as a scientist, you have to ask yourself, are these the result of causation or correlation? Causation is what you want, meaning that there's a physical relation between, when you see this relation here, X drives Y. But in many cases, they're so uncorrelated, it's embarrassing to write a paper about them. They're just there because you, the scientist, modeler, decided to plot these variables that are entirely correlated. So what you need to do to decide if you have a correlation or a causation is to understand your data. I won't go into details, but understand the typical errors associated with your data. And in astronomy, typically 15–20% is the range. Oh, what am I saying? Stop me. Is the range for well-measured quantities. What did I say? The bane of astronomy? Measuring distances. Distances can throw your scaling relations wildly by introducing 50% errors in your scatter. People a lot, as referee, I see that this is ignored a lot. Another one, this is nice because it's not yet astro-related, how you fit the data. Do you use a forward, inverse method, bisector, or orthogonal? What's the dependent variable? Where are the errors? All this, I won't go into details of how you fit and whether you're frequentist or Bayesian and your approach to looking at a problem, but the different slopes and biases that affect your distribution give you large deviations in your slope, scatter, and 0 point. Think about that when you do your fits. Okay, we're really, really done with the introduction. We're going to jump into a little more astronomy and look at some puzzles that the study of these scaling relations tell us. I'm using this Shiver example. There are many, but Shiver is the deepest of its kind today. It looks at galaxies in a nearby cluster, the Virgo cluster of galaxies. There's a few thousands of galaxies in our backyard. We are part of a local group of galaxies that's very essentially attached and very close to this Virgo cluster. The Virgo cluster provides a full range, cosmological range of galaxies, ellipticals, spirals, dwarfs, giants. So it's a good laboratory for understanding galaxy structure. And with various students, these are my students many years ago. Mike McDonald is a faculty at MIT now. He doesn't look like this anymore. But it took quite a while to do this survey because you want to get rotation curves of galaxies, and typically you're looking at an hour per galaxy. So it takes years to accumulate data for just hundreds of galaxies. And it's still, as I said, the largest of its kind. A lot of it was done with some of your favorite telescopes, Palomar, Kitt Peak, VLT Gemini, and so on. Lick, in fact, should be there too. Okay, so here's a first very interesting puzzle. You remember I showed the light profile of a galaxy, and I insisted on the surface brightness. If you plot the distribution of surface brightnesses of galaxies, it's bimodal. My colleague Brent Tully here, Tully and Verheyen, did that. That's their data. This red distribution is what you do when you don't really understand anything. You plot a histogram. You measure these mu naughts here, right? That's the projected surface density of a galaxy. Later we can do a mean, because this is parametric, but we can do an effect. It doesn't matter too much. The surface density tells you how many stars you get per area, okay? And what this distribution is telling us is there's two kinds. However, when I saw this, this is a long time ago, I didn't believe it. First of all, it's small number statistics, and I don't really like bimodal quantities. There's a range. It's very difficult to have a transition that's so clean when you're looking at systems formed by our universe. So I don't like this. I go to Brent and said, this is not the way to do it. I redid the analysis and got exactly the same result. And then we went to Virgo, and to make a long story short, we got exactly the same result. It peaks exactly at the same place. I have to make, I need to move on, but to make, I was still puzzled by the fact that the universe would make two kinds of galaxies. Why is that? I need to understand the physics of that. Other people, yes? Oh, it's not so much that it's, it's not so much that it's wavelength dependent. You want to do this in an infrared band to eliminate the effects of extinction by dust. Okay, that's the reason why we had to use the H band and the K band. In fact, you'll see I'm going to say that, so this was the spiral galaxies. We found the same one in elliptical galaxies, and there, you don't care about dust. There's not as much. So in fact, this bimodality, which is a surprise to us all, has been since duplicated. This is the original work. We reproduced it and augmented it 10 years later. And it's been rediscovered in many other cases, whether you're talking about field galaxies or galaxies that live in clusters. The distribution of surface brightnesses is bimodal, okay? We have a model. We think that a certain kind of high surface brightness galaxies tend to be mostly baryon-dominated in the inner parts, in the bright parts of the galaxy, whereas the fainter galaxies are strictly dark matter dominated throughout. And the ones in between, which for the experts would be Hubble-type SC galaxies, would become unstable because there's comparable contributions of dark matter and baryons. Okay, they're co-dominant in the central parts, and this would lead to an instability that either pushes a system to evolve towards either dark matter dominated or baryon dominated. So if that is true, perhaps we can confirm the luminosity bimodality through a dynamical bimodality. And that's what we did in Shiver, but that again took years, and we did confirm it. So what we're doing here, this busy plot shows elliptical galaxies in red, dwarf elliptical galaxies in yellow. The bimodality is seen in elliptical galaxies. For the spiral, we don't have very much data. There is a bimodality, certainly in surface brightness. This is what Italian company and ourselves confirmed, but this is novel here. Now you look at a bimodality in circular velocity. It certainly exists in the early type galaxies. It's there, but not particularly convincing for the later types, largely because we're missing. These objects are so hard to observe. We're talking about dwarf systems that take hours on the biggest telescopes on Earth. We're currently pursuing this tail with the largest telescope on Earth, which happens to be the Gran Telescopio Canaria, which is 0.3 meters, a little bit bigger than Keck. However, you've not heard too much of Gran Telescopio because it's new. It's a brand new telescope, and it's got just the right instrumentation. Okay, anyway, Keck would do the job. Demos is perfect for that. How are the dwarves defined? They may be defined morphologically, but even better, they're defined by either in concentration, density, color. Okay? And I have another plot for the aficionados that shows exactly the same distribution no matter how you label your galaxies. So what's interesting is this bimodality exists not only between ellipticals and spirals, We know in the universe, ellipticals are red, spirals are blue. That's a color bimodality. That's not what I'm talking about. I'm talking a dynamical bimodality in each galaxy class. Furthermore, another interesting puzzle, you plot the stellar masses of galaxies, that's this m star, how many stars there are in a galaxy versus their circular velocity. The experts in the room will recognize this as a baryonic Tully-Fisher relation. You plot all the galaxies in Virgo and you get your bimodality with a trough here at a specific mass of about 9.5 solar in log, and corresponding velocity here of 2 in the log, which is 100 kilometers per second. There's something very interesting in galaxies at 100 kilometers per second that triggers a system to behave one way or another as far as its dark matter content. Others have found signatures that match this transition of dust lanes in galaxies. Julian Dalcanton, Washington, found that whether you're above or below that transition, you will or not have a dust lane and therefore produce dust in your galaxies. This remains a puzzle because we don't have a good understanding of this particular bimodality, and one way to solve it perhaps is through numerical simulations. What do simulations of galaxies tell us? Drawback is that this is measured on small scales where those numerical simulations are lacking resolution. I'll tell you about 3 more puzzles and then we'll conclude. How much time have I got? Okay. Tully-Fisher. Tully-Fisher is this great puzzle. I'm showing you the deepest Tully-Fisher relation of its kind. If you don't like the names and you're not familiar to it, remember it's a luminosity-velocity relation. And I said it's tight. You may not be impressed. You maybe were expecting a razor-thin relation. But this, nonetheless, is very tight as far as astrophysics go. And the puzzle here is that no matter what the galaxy, give me any spiral galaxy, it will land on Tully-Fisher relation. It's not going to be here. It's not going to be here. It will be over here. I'll show you a quick demonstration of that in a second. So the important part of this slide here is shown in red. When you see this little star, red star, it means this is important. Pay attention. And here, what we want to understand, remember, what do we want to know? Our galaxy formation models must tell us the slope, the 0 point. So the slope is typically gravity. It's Newton's law, right? The 0 point is luminosity, is the star formation rate. The scatter is where all the interesting history lies. And we need to understand that scatter. Unfortunately, the scatter here is dominated by distance error. 50% of it is distance error. We forget that, and then we interpret the scatter in physical ways, but we need to remove distances. So I'll run you through a cute little argument that indicates something about dark matter and baryons and galaxies. We know, we talked about Newton, v squared for a circular orbit is gm over r. M, we can turn that into a mass-to-light ratio multiplied by L, so this is gm over r. I'm going to draw this is purely baryonic exponential disk. Let's try to understand what these disks tell us. For a given luminosity, you'll see why I'm doing that, then I drop luminosity and I get the scaling. And now I'm going to make one assumption, which is standard in our field. The assumption is that the mass-to-light ratio is self-similar in galaxies, meaning that it's not necessarily constant, but whatever the gradient of mass to light properties in a galaxy, it's pretty much similar in our galaxies, and I will eliminate this term. That's an assumption. What do we get? You're familiar with this expression. It's called the Keplerian decrease. That's how planets move in the solar system. V goes as 1 over the root of r. Okay? Well, let's take the logarithmic derivative of this quantity in that one. We get d log v of L over d log r is minus 0.5. That's neat because that's a prediction. We're saying if we start with pure exponential baryonic disks, then their velocities and sizes should obey this relation. And now that you're all familiar with this language, you recognize this as Tully-Fisher and this is size luminosity. And I have to express V of L because I'm measuring these quantities at a given luminosity. I've got a prediction here that if galaxies are all baryons, they should obey this trend. Well, what is and in fact, there's the prediction. This is what we observe. 0, essentially 0. Not quite, but close. The difference between these two is dark matter. Okay? We have a Tully-Fisher relation here. Once again, note how tight that relation here. You have circular velocity and luminosity. These symbols here, the color represents surface brightness. Think of the mu naught that we defined earlier. No matter what the surface brightness, it will always land on the Tully-Fisher relation. That, by the way, is a very powerful argument that we don't fully understand yet. And as I said before, galaxies don't populate this part of the diagram or this part of the diagram. Stability arguments mostly, but complicated ones. You can look at the size-luminosity relation, same thing, it's very tight. D log V, D log R, the D log is basically the residual with respect to the mean trend here and the residual with respect to the mean trend here. And they're plotted in over here. D log V is a function of L versus D log R is a function of L. It's flat. It's not sloped with a slope of minus 0.5. It's flat. Why is that? We'll get to it. You can look at the residual of these relations, right? If you don't know, if you have a linear relation, you want to ask, are my residuals correlated with anything short of having an intelligent model or theory? So you correlate your residuals with size, with color, with concentration, with surface brightness, inclination, you name it. Tully-Fisher does not correlate with anything. In other words, the Tully-Fisher relation is what we call the fundamental plane of spiral galaxies. There's no other projections. The luminosity and the velocity are the most fundamental quantities that describe spiral galaxies. I'll come back to the explanation for that, and I'll show theoretical. Then there's other information, but I have to skip them. I'm also skipping a similar analysis for elliptical galaxies, but imagine we do all this careful analysis of their scatter and masses and velocities, and we put the information that we have for spirals and ellipticals together. This is what's shown in this diagram. Very busy as well, but just brutally informative. We show here the total mass and the stellar mass. Total mass measured inside a so-called effective and therefore non-parametric radius. Total mass measured in its quantity R, 23.5. The experts know that is 23.5 mag per second square. Let's just say the optical radius of a galaxy. So I can measure not infer, but measure the mass inside of the optical radius of all these galaxies. Each point is a galaxy here in the Virgo cluster, and their stellar mass. And I get an incredibly tight relation, and I don't know if you can see in the back, but the slope is exactly 1. You need to understand this with your galaxy formation model. I'm plotting curves here, so-called abundance matching predictions. What that is starting with a cosmological halo and predicting how much baryons should be attached to this halo. That's what these curves show. But those predictions are for cosmological radii. The optical radius is way smaller, so you need to interpolate these predictions. I won't go into those details. It gets a little bit technical. But you basically interpolate those curves into the realm of optical data, and you find that some work and some don't. So for instance, this brown one right here, that actually is not from abundance matching. It's from lensing studies. I know they're lensing. It translates into this form here, which statistically is actually not a great match. So it means that our understanding of halos on large scales and dynamics on small scales still do not match perfectly. This maybe is for the experts, but I want to say it anyway. There are interesting trends that we see between the size and mass and velocity mass that are either bimodal, that's for the size-mass relation. Velocity mass has distinct slopes and distinct between the early types and the late types. And going back to your question, Bahram, earlier, how do you define these systems? Define them by color, concentration, morphological type. You get always the same trends. However, what I can say is theory cannot reproduce this. This is what observation gives you, and you as the theorist need to reproduce it. And we're going to get there in 2 minutes. And this quantity here, the so-called stellar to total mass relation, total mass, stellar, likewise is a mess between the early types and the late types. They seem to have different slopes. We're not quite sure why. Okay? These ones are clean. No matter how you slice it by color, concentration, Hubble type, the trends are always bimodal for early types versus late types. They're all, the distinct slopes are clean. This one here, not so much. That's your stellar to total relation. I put a red star, but I'm going to skip it because it's getting a little too technical for my taste. We're going to continue. And we're going to try to understand what is creating these trends. And that's how I'm going to finish the presentation. So you remember this Tully-Fisher, size, luminosity. I measured the residual in both cases, plotted them against each other, realized they're close to 0, not matching expectation for purely baryon-dominated system. Why is that? Well, when you have a system, a nice correlation, you need to break it down to the various parameters that control that correlate that trend. So with what we're plotting here is circular velocity, luminosity, so that's Tully-Fisher, 4 different panels of velocity-luminosity relation, and here's size-luminosity relation. We know as modelers, I appeal to the galaxy, those people who make galaxies in the room, you typically need 4 parameters to make a realistic galaxy. You need to know the spin of your dark matter. You need to know how much or how concentrated your dark matter is, mass of the disk, and the mass-to-light ratio of the disk. Mass-light ratio informs you about stellar populations for the non-expert. So it's basically baryons here, dark matter up here. 4 parameters. You throw these parameters in your cookbook, and you make galaxies. And then you ask, all other parameters being equal or kept constant, I'm going to change one of them. I'm going to change the mass-to-light ratio. It's going to move me in that direction in Tully-Fisher. If I change concentration, it's going to move me. Ignore the different curves. It's for a web, ignore them for now. Concentration will move you up and down, up and down. Spin will move you in a certain way. And disk mass will move you in a certain way. The quick ones have already appreciated that you have orthogonal vectors, meaning you can turn a knob this way or turn the other one this way, you'll get the same result. But you approach them completely differently. So you still are short of a unique solution. You do the same thing with your residuals. And by the way, I'm sure this style, this approach that I'm showing now is what we do wholesale now in all of our other scaling relations. I'm just focusing on Tully-Fisher. Again, you move mass-to-light ratio, concentration, spin. They're orthogonal. There's no way out. You thought you had a solution, and you're not getting it. Well, in fact, we have a solution, and it's a crazy one. The solution is that perhaps the values that we're using to make our galaxies are not quite right, so we can play with lowering the stellar mass-to-light ratio. But at some point, luckily, we have constraints from stellar populations that tell us you can't go there because then you'd be making a various kind of star that we don't see. Okay, so this is out, lowering initial concentration, out numerical simulations, and lambda CDM suggest that. And these, if we did that, then we'd solve our problem. And by the way, I'm showing Tully-Fisher, but remember, we're trying to solve all the different scaling relations simultaneously. So if I tweak one relation, it needs to fit the others. The only one that works is turning off halo contraction. What is halo contraction? It's nothing else than gravity. The halo, when a galaxy forms, the baryons cool because their dissipation, or they release energy, they cool, they sink to the center of your dark matter potential. They change the shape of the potential in such a way that dark matter is still attracted slowly to the center. We call that adiabatic. It's a slow process, contraction. You drag dark matter in. That's gravity. It has to happen. But we can reproduce all the relations if we turn it off. When my student and I got this result in 2007, that's a decade from now, no one really believed it, and for good reasons, because you don't turn off gravity. However, there's a solution, and it's become a very popular solution. It's to compensate gravity. You compensate gravity by pushing back. We call that feedback. So if you find a mechanism where you can, in fact, counterbalance, if you wish, adiabatic contraction, everything works. The not discovery, but relation that we found has been now corroborated by others, fortunately, but not fully. It's still mysterious, and so I'll say why it's not. I mean, why is it working so well that feedback compensates adiabatic contraction? And I don't have to tell you about the elliptical galaxies, but it's the opposite in elliptical galaxies. Adiabatic contraction is at work, and you don't want feedback, which doesn't quite make sense. Numerical simulations can come to the rescue. And I'm choosing this one that I particularly like. Brook et al. 2012 did just what you want to do. Again, if you're not an astronomer, it's getting a little tedious and technical maybe, but look, what we're trying to do is understand a system and showing multiple facets of our system and seeing if all of them are explained simultaneously. We have a stellar to total mass relation. We have Tully-Fisher. We have what we call baryonic Tully-Fisher. We have specific star formation rates or star formation main sequence, size mass, size luminosity, you name it. There's 8 panels here. We could have more. There's even metallicity. Is our model of galaxy formation now able to reproduce them all in one go? Well, apparently so. If you look at these, the white points are our data, in fact, my data mostly. The yellow dots are their simulations, and look at the beautiful fit. And that simple relation here, when you project it on other planes, seemed to work quite well. However, this is 2012, and still now, we need to cheat. There's no models that actually works that well to this day that actually automatically predicts the scaling relations that you see. In order to work, you need to hardwire some of these systems onto Tully-Fisher. You need to force it first. You bring your galaxy onto it, and you do that by putting an ad hoc prescription for star formation. Kennicutt-Schmidt. If you don't know Kennicutt-Schmidt, it's basically telling you the efficiency of star formation in the galaxy. We don't know how to simulate that. We don't understand star formation. And therefore, our simulations are not going to work too well. However, it's quite an achievement to say, short of, I shouldn't say it this way, our model is maybe not complete, but we're still achieving something great here. I had to fudge a few relations, okay? It's hardwiring something in my simulation, and yet it works pretty good. I don't have time to talk about, so these are all global parameters. When you start looking at the local, your theory and model crumbles a little bit. 2 minutes? -2, 5 even. We're good, we're good. The holy grail of this effort here is to try to predict, of course, the global relations in a unique way and not having to hardwire any particular constraint. Hardwiring physics is good, but putting constraints and boundaries and barriers and limits is not so good. You know, driven by data. We're very much observationally driven at this stage. We're making progress. We'd like to look at the local as well. One final sort of, well, and the local might be, I've told you at the very beginning of this presentation, can we infer anything about the dark matter? I won't talk too much about the nature of dark matter. We could talk about it offline if you'd like. But certainly about the fraction of dark matter in a galaxy, we may remember 1930s, Jan Oort tried to measure the gravitating mass in the solar neighborhood just by asking how fast are stars moving in the solar neighborhood. And realize that they're moving a little too fast for the mass that you infer based on the visible light. There's too little light to explain how fast stars are moving. Zwicky, at the same time, at Palomar, makes similar observations in clusters of galaxies. The velocity of dispersion is too high. There should be dark matter. So we want to know what is the dark matter fraction, very much like Oort posing that question in the 30s, but not just in the solar neighborhood, but throughout the galaxy. At all radii in a galaxy, can we constrain the dark matter fraction? That is a really hard question. But with all the scaling relations that we have, if these models are right, they tell us about the shape of a density profile in a galaxy in order to get at least the global properties. And you can use those to constrain locally the values of V, R, L. So my former student Dutton and I did a similar exercise by saying, we take all the scaling relations that we have and observational constraints and try to predict that dark matter fraction versus, in this case, V total. I'm showing one slide out of many. These are spiral galaxies, elliptical galaxies, and I promised to one of them that I'd say something about lensing. Lensing comes to the rescue. In the 80s and 90s and decade that followed, people were really confused about this question of dark matter fraction. Are galaxies dark matter dominated in the, well, we know galaxies are all dark matter dominated in their outskirts. The question is, as you look inward, some systems, high surface brightness systems, are dominated by baryons, others are not, typically the low surface brightness system. Where does this stop? For a long time, we thought that, and I was one of the guilty party here. My name is here, Courteau, and I kept saying that galaxies were sub-maximal, therefore dominated by dark matter in their inner parts, but, the majority of them. Like our Milky Way. M31, are we dominated by dark matter in the inner parts or not? And it took lensing to clean up this situation because we had a hard time measuring velocities in fainter outskirts of galaxies. Lensing gave us a measurement of the total mass beyond the optical radius. And only then did we realize that for systems that rotate fast, lensing gives you a so-called maximal disk. Right? The fraction of dark matter, this quantity here vetoed, is measured at a position that's comparable to that of our Milky Way, of our sun in the Milky Way. Okay? 8 kiloparsec, it turns out to be 2.2 disk scale length. It's the peak of our rotation curve. So this gives you an ensemble of properties of spiral galaxies, and they're well mapped. And that line here is exactly what the scaling relations predict. So you've got a beautiful model that seems to work, at least for spiral galaxies. Ellipticals are an interesting beast. There's no dark matter at all in the central parts of elliptical galaxies. So then you move on. Oh, this line here is, if you want to ask our own system, this is the Milky Way. There's great debate just to show how much uncertainty there is about our own system. We live in our Milky Way, and yet we have no clue. These are measurements made in 2013 by Bovie and Ricks that suggest that the Milky Way is very much baryon dominated, and yet 4 different studies over the course of the last 5 years have populated this part of the diagram. So jury is still out as far as the Milky Way is concerned. But you can take these models and try to predict what should be the dark matter fraction in a galaxy, any galaxy, as a function of size. For spiral galaxies shown in blue here, you have 2 lines. One, whether the galaxy obeys adiabatic contraction or not. I mentioned what adiabatic contraction was a while ago, right? If the dark matter is attracted by the cooling baryons. So spiral galaxies should populate this part of the diagram. Elliptical galaxies are mostly free of dark matter in the central parts. And as I said many times, all galaxies are dominated by dark matter in the outskirts. So if you as an observer or a modeler come up with galaxies that live here or here, either our model is completely wrong or you've done something wrong. But this is certainly something we need as astrophysicists to answer. Where's the dark matter in our galaxy and how much is there? And our models need to answer these questions. If you like what you heard, there's a great review here that you should consult. I'll skip it, but if you do, all the information that I presented in this 2014 review and Reviews of Modern Physics. Okay, so we're done. The summaries. The first one I did not touch because I knew I'd run out of time. But as scientists, whether we're doing astronomy or condensed matter physics, whatever, we always need to ask ourselves when we see these tight correlations, is this real or not? Difficult question to answer. We saw that there's a dynamical bimodality in galaxies about v-circ of 100 kilometers per second. Why is that? We'd like to appeal to numerical simulations to solve that, but unfortunately, they don't have the required resolution to get there yet. 4 or 5 years, I think we'll be there. Abundance matching doesn't quite work. Do all dark matter halos expand? The scaling relations that we have, you saw that at least for spiral galaxies, the only one way to get a consistent model is to invoke a reversal of adiabatic contraction. Challenging, but possible with feedback. The trouble is that apparently that doesn't work for elliptical galaxies. I didn't talk too much about that, but I'm saying that spirals and ellipticals may have different adiabatic contraction scenarios. So why those dynamical relations so tight? Why is Tully-Fisher independent of surface brightness? We have dirty ways to get to it, right? It's dirty to come up with turning knobs and ultimately finding one that works, killing adiabatic contraction. It's not clean, okay? But there is agreement, though. Multiple teams are finding the same result. From an observer, the wish list, of course, is to acquire deep and extended dynamical profiles for tens of thousands of galaxies. But again, appreciate that it takes hours in some cases to get a rotation curve or a velocity dispersion for one dwarf galaxy. So 10,000 of them will take a little bit of time. We're working on it. From a theorist point of view, as I said, this here, it's definitely a holy grail of figuring out the baryon to dark matter fraction versus radius. Understanding feedback, I didn't go in those details. I don't think it'd be appropriate for this colloquium, but the adiabatic contraction is gravity. There's another quantity that we didn't discuss. It's called the IMF, the initial mass function. It tells you about the fraction or the ratio of low mass stars to high mass stars. And it turns out that the IMF and the adiabatic contraction are directly covariant. You can turn that knob or the other one, you'll get the same result, and yet you don't know what you did astrophysically. So understanding this is very much stellar population theory and observations will allow you to constrain basically how many high mass and low mass stars you have in your galaxies. This is perhaps the most important line here. No matter how wonderful and great your model, there's just no substitute to extensive homogeneous data. And I'll stop there because I think I'm a little bit out of time. Thank you very much for your attention.
So you said if we want to understand this complexity of this scaling relation, we need to turn off this halo contraction, which is caused by the baryon.
We need to compensate. I'll repeat the question in a second. Yeah.
And for doing that, we need this feedback again. But self-interacting dark matter can also do that, can reduce the dark matter central density. So can you comment on that?
Okay, so the question is, when you look at the density profiles of galaxies, if you invoke adiabatic contraction as a way to explain the scaling relations, why not instead let adiabatic contraction happen? It's gravity, it has to happen. And then can we instead invoke a mechanism, in this case self-interacting dark matter, that would naturally provide cores that are less dense? Can I comment on that? Absolutely. I'm all in favor, okay? Why not? It would work so long as you can find a vector, you know, something that works, such as, you know, a self-interacting quantity. This is yet another, when you look in details of the work that you guys are doing and others in this area, there's a number of degeneracies, as we discussed earlier, that prevent you from achieving a final solution that is, I don't mean to say finite, I mean to say unique, unambiguous. So right now, you can appeal to adiabatic compression, feedback. That works, right? Now the feedback, if you like that model, then you need to ask, how much energy do I need to inject? Is this astrophysically reliable? And it is. So it works. Self-interacting dark matter seem to work as well. Which is it? To answer that question, we need to look not necessarily at scaling relations, but actually at the shape of the rotation curves. You know that. That's what you're doing. And I didn't discuss that in my presentation. But it's a horrendous problem because you need to look in the very central parts of a galaxy where instrumental effects are significant, and you need to control a lot. I'm not against it. I like it. I like considering other options. But in order to get there, remember maybe the first third of my talk, we need to measure our observables extremely accurately. So I'll mention, if you know, you have a density profile from R of 0 out to the outskirts. The centers are very difficult to study. There's so many effects that conspire to giving you biased results, such as dust. You need to know that you're looking at the center. If you have dust that's obscuring the central parts of your galaxy, what you're going to be seeing is, in fact, the periphery. Right? Think of, I'm Canadian, so I'm going to use the analogy of a hockey puck. You have a hockey puck that's transparent, completely transparent, and I keep turning that hockey puck. Is my luminosity changing? It's completely transparent. I measure the luminosity of my puck, and it's transparent. No. The luminosity is always the same. The surface brightness will change. The surface brightness will be low when it's face on, high when it's edge on, because I'm intercepting a lot more particles this way than I do this way. The opposite is true too. If my hockey puck is a real hockey puck, it's made of opaque rubber, my luminosity will change. It'll be high when it's face on and low when it's edge on, but the surface brightness will not change. The surface brightness is just the face of my puck. So whether it's face on or edge on, it's still the same density. It's opaque. That example suggests that if you look at a galaxy that has a little bit of dust, I wish I could pick either of these extremes, but in reality, you're somewhere in between. That means that when you intercept the light that's coming from the center, you're not piercing to the center. You stop somewhere along the way. And when you get too opaque, you just see the rim. Okay, if you're really opaque, if you're looking into the dust, and you see the rim. And trying to infer velocities from those kinds of data, of course, will give you biased results. Well, a typical rotation curve goes like this. If you throw dust in the center, it'll look like this, a straight line, a solid body rotation curve. So that's a problem. And not only that, what you're interested in is the very first point. The other ones don't matter. So anyway, that's just one example. I would like it. And wouldn't it be great if it worked? I'm with you, but we need to be careful. Sorry, long-winded answer, but all good. Brian.
I'm disturbed by the
Bimodality. Okay.
When you had a plotted acquisition very early on, you had the morphological types in different colors, and the bimodality happened right at this transition between different types. I just wanted to make sure, is this one uniform selection of galaxies, or is this multiple selections, and this bimodality is happening at an interface between the selections or something?
All right, I will repeat the question in a second, if my fingers could be more agile. And I will show, I don't know, say maybe this one?
Yeah, there was one where you had
The velocities as well? This one?
yes.
Okay.
Yeah, that's exactly.
Okay, good. All right, so, how do I? The question was, I'm looking at the camera, is whether this bimodality results from sampling bias, right? Did we sample the populations in different ways? And we didn't. That's the beauty of it. And not only did we not do that, but other people after us also redid the experiment in other kind of environments and found that bimodality as well. This is one single environment. It's our neighborhood, the Virgo cluster. We take everything, the kitchen sink. We take everything there is to be seen. Unfortunately, the fainter ones are hard, right? But at the brighter end, we're pretty complete. What this means is very, you know, the Astro 101, we're taught that you can Hubble classified galaxies by morphology, and we have these spirals and ellipticals and lenticulars. But amongst the spirals, there are different kinds depending on their spiral arms and size of bulge. So if you have a big bulge, we call them SAs. Small bulge, we call them SDs. And what this bimodality here tells us is that there's very few SCs, okay, in that language. Here, unfortunately, it's not maybe the best diagram to show you because Virgo is incomplete for us. At least, sorry, Virgo is complete. Our observations of Virgo are not complete. But I have many other examples based on these. The reason why you don't have so many points here is because I could only show those that have a velocity dynamical measurement associated to them. But if I stick with just photometry, this is Virgo right here. And here I have hundreds. And my bimodality is very clean, very clear, okay, very strong. And again, it's showing that, you know, we're short of SC galaxies. That's the bimodality for spirals. And it's not due to selection. It's not, but again, for Bahram's question, if we had done this in the optical, say with Sloan data, you need to do two things. You need to make sure you have a volume limited sample and you're not affected by dust. The example of the hockey puck applies here as well. But in addition to the bimodality for spirals, we get one even stronger in the early type systems. That one is very puzzling. I don't really have a model for it. And we're fairly complete. We punched on these dwarf ellipticals quite hard, and we got a lot. So we could get fainter ones, but we'd just be getting more of a tail. The bimodality is there and strong. So next is understanding it dynamically. And I'm dying to do this with numerical simulations, but we don't have the resolution needed for that. When your simulation gives you a resolution of 1 kiloparsec or so, and you realize that that transition in galaxies where you have equal parts of baryons and dark matter is about at that scale, you're in trouble, right? Simulations are not just accurate yet, and let alone the fact that simulations do not reproduce the scaling relations. That's a problem, right? So if we can't make realistic galaxies just yet, I don't want to diss all the great work that we're doing with numerical simulations, but a standard problem is we're overcooling. We're making cores that are too dense. And so our galaxies are not quite realistic just yet. Scaling relations are just exactly the tool that you want to calibrate your scaling, your simulations. And given that the match is not so good, we can't just explore this problem just yet. But all puzzles that I mentioned, 3 or 4 of them, there are many more, they will soon be resolved, I think, within the next few years. Once we understand the true nature of dark matter, whether feedback works, how we transfer, how you take energy. Suppose that it's feedback. The question is, I thought this would, how do you impart energy into the dark matter? How is that process happening? Well, it's dynamical friction does it, right? So you need to have, and we think we understand it. Numerical simulations help us, but we still have a long way to go. Well, 4 or 5 years. If you're a student, it's a fabulous field to be in because things are moving fast. And let alone the other work that we're doing at Queen's, pinning down the true nature of dark matter, if dark matter it is. I mean, some of our conclusions depend on our assumptions about the dark matter, whether it's cold, warm, fuzzy, self-interacting, will affect some of these conclusions. Some of them will be degenerate, and we'll need other kinds of diagnostics to pin down the unique model of galaxy formation and nature of dark matter. Thank you very much again.